Okay. So these are what my residuals look like. Okay, so here, so why do I plot those residuals? This is the red line. Okay, the red line is the line that has the estimators there. If I really wanted to know what my epsilon i's were, I would have to draw the blue line with the A star and B star, and then see how far my points were from the blue line. So those guys are not my epsilon i's, but they are some sort of epsilon I hat. All right, so they're close to it. If my red line is close enough to my blue line, then this should be close enough to a realization of the random variable epsilon I. Okay, so it's kind of a weird notation because it's an estimator for a random variable, which is a really odd thing to do. Okay, but what's nice about this is that once I have those residuals, they're close to being n IID realization of my random variable epsilon I, and then I can start doing inference about epsilon I. What can I do with epsilon I? What would you be tempted to do once I give you all those values, this value, so even with the sign, right? Because I know whether I'm above or below this curve. So I give you those IID close to estimations of epsilon I. What would you want to do with it?
I mean, first we want to check the expectation of that, or like if we average those, is it close to 0?
Oh yeah, that will be equal to 0 by construction, right? Because so what happens is that, right? So this is precisely because the red line is actually not the blue line. If it was the blue line, they would be close to 0. But since it's the red line, it's actually exactly equal to 0. So you can actually prove even that if you look at the average of the epsilon i's, it will be equal, epsilon I hat, it will be equal to 0 by definition, just from the construction. Yeah, we can definitely try to figure out the variance, right? I could look at the sample variance of those epsilon I hat. And if I do this, that would give me an idea of what the variance of epsilon I is. It turns out this will actually be a good estimator, and we'll see that when we talk about multivariate regression, this will follow as a simple, the one-dimensional thing when we have only one x will actually follow as a simple corollary. What else? Yeah? Okay, so what would you do with this? Okay, so we have a distribution of epsilon i's, right? And what I'm typically, so you're asking, I'm trying to do inference about this distribution, and you're saying just look at the max. Okay, so that happened, we did that only once when we were trying to estimate the parameter of a uniform distribution, right? But do you think it's reasonable to assume that the epsilon i's are uniform? Probably not, right? Yeah?
Like see whether they look option or
Yeah, how would I do this?
plot.
Exactly. So you could do a QQ plot. You could take those guys, do a QQ plot, see if you see some tail behavior that looks normal or not. You could even run some Kolmogorov-Lilly force test if you really wanted to test whether they were Gaussian. You could do a bunch of things. Okay? And so there's a lot of things you can play around with when you want to do this. And if you actually run linear regression in R, which is what I use here, all these diagnostics come for free. Okay, there's actually something that says, so basically there's a software which is LM for linear model. You say LM. This is how hard R is. So you do LM of y given x. Now you store this into some variable. Let's call it A. And then you could do something like plot A. And what it's going to do, you just press enter. It gives you a bunch of plots, and one of them will be a QQ plot. If you do summary A, it will just summarize a bunch of things for you. The value of A hat, the value of B hat. It's going to perform a test whether those guys are equal to 0 for free. It's going to do a Kolmogorov-Smirnov. It's going to do a million things for you. This is so standard that they don't even ask you what you need. They just throw it at you.